software based.
You mean like completely just using the GUI to do it?
Mm-hmm.
I was curious because it almost made it seem like they'd go into more than that. It looked like the guy in the past who had done it is teaching at San Jose State now, so I'm not sure if he's still teaching here. So yeah, I was curious if you knew actually who was going to teach it.
I didn't know. It's a little bit of a, I think scramble is probably the nicest way to put it, since Mario is not helping in the office anymore, and Troy is there, so there's a lot of new folks involved in the department for getting classes structured and things like that. So I think there's a little disconnect there. They hadn't had it sorted out ahead of time like they normally do. So, okay. So this is our last time meeting. I don't know if that's a good thing for you or a bad thing for you. But either way, it's our it's our last time meeting. I'll put together a little thing we'll call a final. Like I said, I'll try to get it out this week. If not, make it available this weekend, and then you'll have like a full week to do it. But it's basically, going through your notes and things like that. So you should be well prepared for that. Yeah, nothing to stress about. So this class was more of a kind of an informational, like a real graduate level class where we were talking about things more than actually having you run through academics and things. So hopefully you actually picked up a lot of conceptual topics and understand them at a high level, at least enough that if you decide to get into finite element methods or anything like that, you can go in deeper on the topics. So as such, what I thought I would do tonight, instead of showing you that last hand problem, is I was going to just kind of briefly go over the MATLAB code that I did when I took a finite element class at Davis, and it's a one-dimensional code. It was actually a homework assignment, and I had 2 weeks to do it, so you're going to soil yourselves when you see the code because it was done in 2 weeks, which is a little crazy. And we're working full-time doing it, which is even more crazy. But what I like about this problem is you'll be able to see the strong form problem in the code. So you can see that. And then I broke it up using, it's in MATLAB, I broke it up using functions. So it calls different functions, even though I didn't need to do that, but I was kind of starting to think about something much bigger. So it's one-dimensional. But what the exercise was to compare a closed form solution for the typical strong form problem to a finite element solution looking at a linear element and a quadratic element. And remember, that's referring to the shape function. And we can pick the number of elements over a given length. But the one thing that we actually didn't get into talking about is one of the sanity checks is you check the derivative of the exact solution compared to the finite element solution. And it's a sanity check of how much error you have by looking at the derivatives of the solutions as we go. So I hadn't looked at the code in a long time, so I was trying to get brushed up on it right before you joined here. So let's maybe a place to start is kind of are you able to see my screen in the Windows Explorer?
Yes.
Yeah, we can see it.
So the way I structured my code is, like I said, I did it in functions, right? So each one of these is its own M file. for area, for body force, element force. That's the force that we're being applied to it. Element stiffness, exact solution. This FEM1D, that's actually the primary code for doing the solution. Gauss points, these are Gaussian points. So that's part of that, that Gaussian distribution for getting our solution. The Gauss weights, the weighting functions, and then what my Young's modulus is. So if we go, so I took this over winter in 2018 is when I did this code with this guy Sukumar. He's a really good guy at UC Davis in finite elements. So as this is like a single homework, which is crazy. But it's a one-dimensional, and here's the problem right here. I mean, are you able to see this? The EAU prime quantity prime plus B is equal to 0. That is the problem we've been talking about, right, for the last weeks. This is the problem that we're trying to solve. Omega is my my boundary or my domain from 0 to L. So it's just, you know, a line, 0 to L. E of X, I'm defining as a Young's modulus. And A of X is a cross-sectional area, and B of X, as we've talked about, is the body force per unit length. And now, you know, we're setting up some boundary conditions. We're saying U of 0, so our displacement at 0. So that's our fixed boundary, right? So that's our wall that we've essentially fixed. Is equal to this, you know, just basically creating a variable here, and that's the essential boundary condition. And the derivative of that is our of our EL U prime L is equal to this sigma naught. This is our natural boundary condition. And we're a finite element approximation. And you notice I used the word approximation. This is something that I got, you know, kind of slapped, you know, my hand slapped for. I called it a solution at one time, and my professor was very good. He, you know, really was beating this into us that this is an approximation. It's an estimation. It's an approximation at best. And don't give the audience that you're talking to the impression that you think that this is an exact solution, because it's not. It's using the Galerkian method with a linear code, or part of another homework was we actually turned it into a quadratic form. So I'll show you that difference there. And then L is the length of the bar. Num L. I didn't get into any of this explicit language, I don't think, with you. I might have, but it's typically language that would be used in Fortran for calling these things out. But this is basically just the number of elements, and nodes are assumed they're equally spaced. U sub 0 is the boundary condition at x equals 0, like we said. The stress at the end at x equals L, so that's the free length n, if you will. We're defining that. Element type, this was initially coded as linear only, but since modified it to where we can put a quadratic in. And then these are some just defaults that I had hard coded in it for trying things out. L equals 3, num L, number of elements is 3. Bound displacement at the fixed end was 0. Stress at the end, free end was 1, and then linear type. But I broke this up into different functions to call these things in. So if you look, I have a separate tab here for my Young's modulus. So E of X is equal to 1. We know now, because we took this class, this E of X could very well be C, right? It's our C matrix, and it could be how many elements if we're talking about an anisotropic material, a full material?
81.
Yeah, it can be a 9 by 9. So I'm assuming that what type of material am I assuming by just having a scalar here?
Linear isotropic.
Exactly. So I've got my linear isotropic material property here. This could be set up as a matrix if we wanted to. I'm going to jump around. I have my cross-sectional area just set up as 1. This could be a function, the way this is coded, or what we've learned. This could be a function of, it could be a tapered beam. So it could be really large at the boundary condition and slope near to 0 at the free end, or it could be the other way around. Our body force, our B of X, again, this could be a function. I have it set as -2, this because we were given a problem to solve that had some values in it. So -2, again, this could be a function. Element force, this one's a little more involved here, where it's pulling in the Gaussian points and Gauss weighting. If you notice this n right here, so this is n for linear and then for quadratic. These are the shape functions. Do you recognize these? 1/2 times 1 minus xi to the I, half times 1 plus. You should recognize these as shape functions. This is the linear shape function. This is a quadratic shape function. And down here, I have, I'm defining my B of X as my body force, X of G. But see my force, my forcing function, it's my Fe plus my weight value. And then here's a Bxn times the determinant of J. So these are all, should be familiar forms and terms that we went over, that you saw. Gaussian points, this is something that, I wish I came up with this. He felt sorry for us and gave us this Gaussian points. But these are just the points defining where those integration rules are going to take part, as well as this Gaussian weighting function. He was kind enough to share this portion with you. I would have given you guys this code, but I can't give you his stuff here, so it wouldn't have worked without this. Okay, so we've got our setup. Hopefully all of this notation and things like that are ringing a bell to you. They're very common to what we were talking about. So that's how we have that set up there. Now, where did I have this? So here's my main function. L is equal to 1, ml is 4, sigma 0 E-type linear. Okay, let's just solve this. Let me hit run. And are you able to see these plots?
Yeah.
Okay. So are you able to see that the Fe solution, that's the finite element solution, is the blue line. The dotted line is the exact solution. So I have an exact integration in here. But do you see that it doesn't line up completely? There's definitely error in there. And look at our derivative compared to our exact derivative. See how it's a step response? So what would this tell you with regards to results? Let's look at here our exact solution and our Fe solution are lining up here at x equals 0.25. And what will we cross here? 0.25. So looking at the derivative, this is what I wanted to show you is looking at the derivative is a way of indicating where in our solution we might have better agreement. Our derivative is crossing our exact derivative. we have a very large swing right there, right? We can be on either side of it. So it's just an indication of where you're at. So let's change this number of elements to 2.
And that's literally like saying we have now 2 elements
Yes.
in this 1D problem.
So we have a 1D problem, a beam, and it's broken up into 2 elements. And see the amount of error that we have here between an exact solution and an FE solution. So depending on what you're doing, right, the error, I don't know. I mean, this is displacement is what we're predicting here in the solution. We're plotting UH of U. So this is a displacement. Right in the middle of the beam, we're doing okay. But you know, at 0.25 and at 0.75, we're pretty far off in our derivatives aren't even close with that. So what's interesting is if we bump this up, and let's say we have 20 our displacement solution looks pretty good, but our derivatives are still off, right? So we've got, you know, it's kind of bouncing back and forth where we have these now. How is this going to show up in a solution, these derivatives? What do you think? Remember the Jacobian? The Jacobian was the partial derivative of our mapping from our X domain to our C domain. It was that mapping and those derivatives. So if we have inconsistency with our derivatives between an exact solution and in our FE solution, what you're going to see, this kind of stair step thing, is what you're going to see in your solution is you're not going to see continuous results. This is where you're going to get, you're going to have results where it seems like you could have a hot spot or a high stress and then a lower stress, and there's not a smooth gradient between them. It's where it's a really steep gradient. So this is linear element, and that's what that is. If we change this to, so that was a 20. Let's change this back to 1. And change this to quadratic. Look at the difference. They're like spot on to each other. And that's just with a single element. So kind of the punchline to this is typically, wrong mouse. I'm going to try to open. All right, we'll open the. Are you seeing the Microsoft board opening?
Yeah.
Yeah.
So I think it's easier to talk about, well, we're talking about a 1D element, right? So we're talking about a single element, and we're looking at linear. so we have our shape function, right? That comes up here and then drops down. Shape function comes up and drops down. If you remember my code, I said that the nodes were equally spaced. I wasn't specifying the number of nodes. I was specifying the number of elements and just saying linear or quadratic. So what's meant by quadratic for the example that we're doing is, again, you have a single element, but now we have a mid-side node, and we have a shape functions that look like this. But also, it has to do with our integration rule. Remember, our element formulation was not just the shape functions n. These are n1, n2. These are n1, n2, n3. Element formulation is our shape function, but it was also our integration rule, right? So in this linear one, assuming a 1D, where's our integration point? Right in the middle. I think we showed them as X's, right? Do you remember where our integration rule was if we had a single element with 3 nodes?
1 over square root 3 or something.
Yeah. Yeah, it was kind of like 1 over root 3 and minus 1 over root 3. So we have two Gaussian points and another node associated with it. So that's really the difference, right? It's our shape function and the number of integration points that we have in the element. So we're basically discretizing. Way of thinking about this. I like to think of it like this. Let's say we have a stress strain curve. Let's say we have a monotonic stress strain pool, and that means pools to fracture. This is called a monotonic pool. It's a one-time pool. So this is our sigma y, and this is our sigma tensile. If we wanted to represent this this line in a linear fashion, like a piecewise linear, we could break this up into linear points, right? You can go from here to here to here. I'm exaggerating being off the line because my artwork is horrible. To here. And you see it gives us a similar approximation that we had with our exact solution with our FE solution when we had a low number of elements and we had a linear approximation. So it's basically the same thing as when we're doing this linear. It's almost like a piecewise linear fitting function that you're doing to an exact solution. So it's almost like at an elemental level, versus the quadratic is almost like a more of a mathematical discretion. So here we're doing a more of a geometric, because each one of these lines is a line segment, and you know it'll have a coordinate system associated with it, so you can write an equation for each one of these independent lines. So it's more of a geometric piecewise function that we've come up with, where the quadratic is a mathematical way of discretizing it. So in this first one here, we've broken this up into 1, 2, 3, 4 segments. We're saying, okay, we're gonna linearize this problem using 4 segments or 4 elements, if you will. And that's going to give me a certain agreement. But you could do this the same thing using a quadratic. You could say, I'm going to break it up into 4 elements, but I want each one of these elements, instead of being a linear line segment, it's going to be quadratic and it's going to be fit to this function. So the idea of going from linear to quadratic, maybe don't think about it quadratic. Maybe think of it as a simple integration rule to a more elaborate integration rule, meaning more integration points. And it's a more detailed integration rule. You're going to get a better solution. You're going to get finer resolution to it. Is that, you guys kind of follow that train of thought? It's like a finer resolution to zooming into your problem. It's not something that you have to do. You know, the problem that I showed in MATLAB, was there a problem with running 20 elements and getting that agreement and getting a stair step as the as a derivative? It depends on what you're trying to achieve. Now, where this will come into play when you're actually dealing with this potato is so this is, you know, each one of these segments is an element, right? And it's going to take so long to solve this problem. But let's say that you're using a linear element and your solution doesn't look right. You have really large gradients in your result, meaning a really high stress next to a really low stress. And you know that there should be some transition there. Your only option is going to be to either switch from a simple integration rule to a more extravagant one. Like, so go from a single, go from, if you're doing a single element with a linear integration rule, bump up your integration rule to 2 points, and you keep your mesh density. Or you can keep a linear one with a single integration point, but you have to increase the mesh density, right? Which means now you're adding more elements. And it's a trade-off for depending on what you want to do. The simple elements, the ones that are linear shape functions and have a single integration rule, the lower number of integration rules that you have, are going to solve faster computationally than the ones that are more extravagant, have more integration rules or more integration points than others. So it really depends on how long you can afford to wait. And so it comes down to, you know, let's look at a 2-dimensional element that has a single integration point versus one that has 4 integration points versus one that has 1, 2, 3, 4. So you can do that, or you can say, okay, I still have this box and let's go like this and still have single ones. Hopefully you guys are following this crazy logic.
Yeah, that makes sense the way you're explaining it between linear and quadratic.
So I'm not going to fit 9 by 9 when I do it this way. I'm not going to be able to write it that small. So hopefully you get the gist of it. So this column here is going to solve way faster than this column here. So if you're designing a belt buckle or something, you know, and you have 2 million elements in your belt buckle, and you're like, yeah, I'm the cool guy. I'm going to use this 9x9 or this 3x3 Gaussian rule to solve my belt buckle. You're going to be waiting a really long time for results, right? You're using ANSYS at school. It's not going to work. There's going to be too many elements, and you're going to crash it. And if you're using it at work, you're probably going to get fired for using computer power that long for something stupid. But the point is there's a balance. There's a balance. And what you want to do is you want to start off with this. You want to start off with something very simple that's fast, that you can actually get a solution. And what you're trying to look for in making sure that you actually get a solution is, one, does your software system error out? Does it give you like a free body motion or a Jacobian error or something like that that tells you that maybe you have a problem with your setup? Maybe you're missing a material parameter. Maybe you're doing something silly like you have you have a fixed boundary condition, and you have a beam or something, and maybe you've used SolidWorks and you have a joint or something, and this thing is swinging around. You're not going to get an FE solution based on that. It's called free body motion. It's not going to work because this would have to be kind of fixed. Solve it with something that's quick and easy to say, are my boundary conditions right? Am I getting results that seem reasonable? Are the high stresses in the areas you should be getting high stresses? And then once you've done that and you need more fidelity, then start heading this direction to get better refinement in your results. And it may be like in this particular thing, maybe all you care about are the stresses, right around this hinge, and you don't care about anything out here or out here. So maybe these elements and super coarse elements out here are perfectly fine because they just have to exist. They have to be there. And you want super, super dense fine mesh in here. And maybe you want some of them quadratic or, whatever it may be. You want to make this as an intelligent decision. And I always think of it almost as like spending money, right? You start off super cheap, you try it out. Yeah, am I going to like this? And then you kind of add more complexity or more detail as you need to. Because if you get into work and you start doing this stuff and you jump right into these really high order element types, really high density, and you're trying to troubleshoot your model, it's kind of like trying to troubleshoot this MATLAB code. You have to start with small, single couple lines at a time. You run it, you check it against something you've done by hand. It's really the same thing. You're decoding your finite element work to make sure that you've set it up right and you have everything working cohesively like you planned. Okay.
So kind of curious, I just want to poke at this. So there's no way that you can kind of combine linear and quadratic in the case of that beam that you showed. So if you're interested in that region, you can only
It depends. No, it depends. It depends on the software that you have. Some softwares won't let you mix element formulations. I've heard of in a part. As long as you change the element density, they usually let you change it within that density. But it depends on the code that you're using.
And just like another follow-up question, do you see like a lot of people using like going into the code, like the back side of things?
You're locked out. You're locked out. So you're completely locked out of it. So ANSYS, Abacus, Nastran, the actual what I'm showing you here, the actual finite element solution, you're locked out of. You can't touch it. You can do scripting with it where they give you the commands to put inputs into it and you'll get outputs out of it. So you would either have to manipulate the input coming in, knowing how this finite element mathematics work to get a different output. But I'm pretty sure all of them, well, they will. They'll allow you to design your own element as an input. So you can actually create an element with your own shape functions. So your shape function, was like a function, right? It's something that, I told you what it was, but you could define your own element type, which is a shape function, integration rule, the whole deal. You can customize and build your own element, and that's an input into this black box. They usually call it the solver. So that could be a parameter that you're pumping into the solver, and then you get an output. In fact, like in the lab, my lab partners at Davis, or at least the guys that are lucky enough to do that there full time, that's how they work. Is they work with MATLAB and they call the Abacus solver to do things and then give them the report back. They don't actually use the Abacus GUI or actually look at any of the geometry in a GUI window like you would like in a CAD frame or anything like that. Everything is just the mathematics based. They have all of the call functions and to script directly to Abacus. So they'll define their own elements, what the boundary conditions are, what the input parameters are, and all that. That'll feed into the black box Abacus code. It computes the finite element solution based on those parameters, and then gives them the output, and then they continue the computations based on the output results. And they actually create a loop because they're doing crack propagation work. So they get a stress result and as an output, and then they evaluate it and run that through the J2 flow theory to see, is it plastically deformed enough at the crack tip to where it actually unzippered and opened it up a little bit, modifies their boundary conditions, feeds it back into the solver, and they do it. It's kind of iterative solution that way. So it really just depends on how theoretical the work that you're doing. At Siemens, we go from, I'm going to oversimplify it, Jacob, so I'm sorry. We go from Creo, which is Pro-E, so it's equivalent to like a SolidWorks, right into the ANSYS environment. You mesh it, you solve it, and you do all of your manipulation within the ANSYS environment. It's quite a complex process. That handshake, and it's very tedious, and there's a lot of places that you can screw it up and get totally bogus results based on either modeling decisions or errors that were done in Creo, I don't want to say bad, boundary condition decisions that you made in the software environment when you set up the ANSYS job, like fixed boundary conditions, or is something, contacts, is it a bonded contact, is it a frictionless contact, like this joint right here, right? There's different ways you could define this pin. You could say that it's fixed, but if you say it's fixed, it's infinitely rigid. It actually really changes the stress results, versus if you changed it to a frictional contact, then this thing's going to swing. So it's one of these things that people look at this whole idea around finite element analysis and the output of it, and they think that it's this ultra precision like tool, and it's really not. It's really, it can be if you really know what you're doing and you really take care of your assumptions that you put into the model. But if you're sloppy, it can lead to really unsafe results as well, that you could make bad design decisions based on.
Yeah, and to your point, most cases in like in my limited experience in like industry, what happens is you have like multiple people from different, like you have a heat transfer guy working with an aero guy, and so keeping the like mesh simple enough so that each of them can get it to converge in their different like environments is that was always like all the meetings was like the aero guy wanted to progress his analysis, but the heat transfer guy like couldn't quite get it to converge or whatever, you know.
Mhm.
To keep it so simple as possible in terms of the meshes.
And they were using the same model.
Yeah, well, they were they were designing a new fin for a missile, so they were like starting with a brand. It was a in-house created model, so that they kept coming back and had to retailor the like all the dimensions and everything were open, right? So they would all agree on a thing and meet up and then like readjust it and do a new analysis. And the heat transfer was always like the last step, but I think that was always the hardest. I don't know enough, but
There's there's trade-offs. There's definitely trade-offs, and sometimes you actually make modeling simplifications to supplement or to help your analysis to make sure that you can get a mesh and you make sure you can get a convergence and you do solutions. And you need to do that knowing all of this stuff, right? Knowing, am I making a simplification to my geometry to get a mesh? Am I doing that in a way that is safe for whatever it is I'm doing?
Right.
Yeah, so it's an interesting process for sure. So does anyone have any questions? Hopefully you're not bored.
I was wondering, could you like, I don't know how to explain it, like improve the resolution of the graphs from the code if you were to go for like cubic shape functions, like going up a step?
Yeah, so remember, these are all of our assumptions that went into this were based on basically the whole idea of a power series and only looking at the first couple terms because they were the most meaningful. That whole concept plays into our shape functions, our weight function, our Gaussian integration rules. Those are all essentially power series expansions. Every one of those topics was like a power series or a Taylor series expansion, where we're only taking the first couple terms, right? So if we take the first term, it's linear. If we take the first and the second, it becomes quadratic. So yeah, if you take more terms, it's going to get more accurate, but what happens to your solution time?
Yeah, that's kind of what I was wondering is like, is quadratic kind of where the cutoff between efficiency and accuracy starts to come into play?
It really comes down to your computer and what you're trying to do. Because ultimately what you're doing is we're solving that K matrix, right? That's what we're solving for, is that stiffness matrix, the K matrix. And in order to solve that, with the FE solution that we presented today, you have to do a matrix inversion and you have to transpose it. So it's that inverse matrix flip. Solving that equation takes a long time computationally. So if you have more elements, that's going to take longer. And remember the terms that are in that, if those terms are those B terms, and those B terms are a function of the shape function or weight functions and all those. So if you have some crazy functions in that B matrix that you have to solve as part of your inversion, it's going to take forever. And then you have to try to figure out, okay, how are you going to split this up computationally? Are you going to use like a GPU to try to do some of that processing? Is some of it done on your local CPU? Then you run into like local RAM issues, depending on how much you need and how the code is handling, all the codes handling, storing that for the solution, because it's going to store all of that information in local RAM, right? While it's accumulating more and more, trying to get the solution. So your processing time goes through the roof.
at my first job, we used ProEase Mechanica for FEA, and in order to keep the mesh the same through each, in order to converge on a solution, we refine the solution more and more each time until it reached a certain convergence. We kept the mesh the same, but upped the polynomial order of the shape functions each time. So that way you never have issues redoing the mesh in between each iteration. And it worked pretty well. So just keep upping the polynomial order of the shape function until it converged.
Yeah, and SolidWorks does that. It's called
P elements.
P adaptive, I think.
P adaptive, yeah.
Yeah, P adaptive, and it'll increase your polynomial order, and you can set ranges of how much it'll increase it. And it has a H adaptive, I think, which is just
I think by default it's H adaptive. Most programs are. By default, Mechanica used to be, at least by default, P adaptive.
Yeah.
What is H adaptive?
Was that?
In SolidWorks, H adaptive, I think, is element density.
Yeah, it'll increase element density until it converges.
Mm-hmm.
So
with the keeping this shape function, you're saying there's like,
yeah, it's basically like if you have a linear element, it keeps it a linear element and just increases the number of elements.
Gotcha.
Yeah. So it's really about just knowing what you're doing, and I think it's important to know the mathematics behind it. Right now, I mean, hopefully you have a sense for it, right? You have a sense for what the heck is going on behind the scenes, and it helps make decisions, for you. And when you're troubleshooting code and things like that, like when you see an error and it says something about a Jacobian, you know what the Jacobian is now, and it's like, okay, what's going on? This is something with my mapping between a coordinate system, a local, and the or your element between your two zones, and more importantly, it has to do with the gradient of that. So it's probably something wrong with your model. I guess we could have skipped the semester and just said that, right? But hopefully it gives you a little bit, sharper tools for doing this work. So. Any other questions?
I feel like deep down I have questions, but like I need to process it.
I don't know if any of you are like me. I'm really dense. It takes me a while to get stuff. So like I said, I took a lot of classes in this, and I don't think I really started kind of getting a grasp for it until after I was done with all of them, and it was really starting to sink in and really think about it. And unfortunately, the thing that I really don't like about my job at Siemens is I don't get to do this stuff every day. Jacob does, which is awesome for him. I'm like super jealous. He's getting to do that stuff. So I don't
reports half the time though. Reports.
What yeah.
There is reports half the time though. So
yeah. So I don't get afforded the time to play with the models and do the analysis in detail all day, every day. But I still think it's important to help, understand what's going on and troubleshooting things. And
yeah, I think definitely the hardest part is that it's all like what you're doing is trying to help us build intuition, right? But what it really comes down to, like, you need a ton of practice to get a feel for like, what is, if I see this error or this problem, like, what do I need to try adjusting, right? That's definitely the hardest part. Is I've been exposed to these topics a lot, but it's like very limited practice, right? Like there's projects where you do and you're just scrambling to get them done, and then afterward trying to think about it. But
well, you're more empowered now. So if you sit down, I mean, the thing that always concerns me, especially like SolidWorks, it's so intuitive. Like when I've taught 177 or whatever, you have people going through and doing their senior projects, and they're doing FE analysis in SolidWorks, and they have totally bogus boundary conditions, and their analysis models are set up totally wrong. But they've got results, and they're making decisions based on those results, and they're not good engineering decisions based on that, because they don't really understand how big of an effect a fixed boundary condition is versus a frictional boundary condition, and what that means for that whole finite element solution, and what the tractions are, and making sure that the tractions are defined everywhere, and knowing that we went over that quite a while ago, that traction is your boundary condition, right? You have to have a formulation over the whole surface. And when you define a traction in one spot in your part, and you don't define it anywhere else, that finite element code that you're using, ANSYS or SolidWorks, is making a decision for you, and it's applying a traction. It's just not telling you what it is it's doing, right? It's usually nothing. It's usually setting it to 0. But a lot of people don't even realize that. They just think there's nothing going on behind the scenes. I didn't touch that surface. I didn't select that line. There's nothing going on. Well, guess what? There is. There's a traction. There's a decision being made, good, bad, or indifferent, everywhere around that body. So,
Yeah, chasing your tail.
And then the other misconception, which I think is really funny, is, and hopefully all of you know this, what is the output of a finite element solution?
An approximation.
Yeah, but what approximation of what?
Stress?
Displacement.
Oh yeah.
Oh yeah. Cameras are funny. Displacement. That's what the solution is displacement. And when you have displacement, that's delta L over L, right? You've got strain. And when you have strain and you have your material modulus, you have stress. It's Hooke's law. But the output is displacement. That's what you're solving for, is a displacement field. All right. Well, I think that's all I have for you folks. Hopefully you've enjoyed the semester and got something out of it. Yeah, look for a little final type thing come out at you either tomorrow night or over the weekend. It'll probably be over the weekend. But I'll give you like a full weekend, the following weekend to do it and submit it. So like I said, if you go, it'll be in chronological order. So if you go through your notes and go through it, you'll be good to go. It's just something to get you points so we can justify your awesome grades that you'll get.
So if you're gonna walk away from this class with like 2 points of information, what would it be?
Finite element approximation is the output of it, and don't trust the results. Question them. Don't just blindly take them. Did that not satisfy you?
No, yeah, that's fair. I'm looking at my solution. I'm like, does this look right? Does the stress look right here?
No, it's you guys are and gals you're engineers. You have a beam and it's fixed here, and you apply a load here. If your high stress is out here, you have a problem, right? Your high stress should be at your boundary condition where it's fixed. It's just use your base knowledge that you have, of mechanics in your undergrad, and then start, okay, what's going on with this finite element junk he's been talking about for 16 weeks? I need to get better results in this area. What can I do? And try to force yourself to think about the math. It's all the same problem. That EAU prime, take the derivative of that plus B is equal to 0. And in all of the problems that we kind of sprouted through, conceptually went through, we had no body force, right? B was 0 because that's pretty much just a magnetic force. But it exists, it's there. It's another force term that exists. So I think just understanding that will go a long way if you decide to go in this field for research or anything. So. All right, folks. Well, I wish you a good rest of your program and a good summer break, and wish you guys all the best.
Thank you, Professor.
Yep. See you, folks.
Thank you, Professor.
Yeah, thanks.
Thank you, Professor.
Thanks.
Fun,
Professor
fun
McLean,
semester.
is there any, I hate to catch you on the end here, is there any chance for whatever reason my CPU is blurring when you were going through the code and just kind of showing the MATLAB? And I think I may have fixed the problem. Is there any way I'd be able to glance at that?
At my MATLAB code?
Yeah, the problem solution. I kind of was having trouble following through with it. It was just kind of blurring as you were talking. I had a screenshot of it, but I think I might have fixed it.
Are you talking about just the plots or?
Yeah, well, yeah, I wasn't able to really see the code at all when you on your input. I could see the plots, but I was having trouble. Yeah, it seems to still be coming through blurry on my end. Huh.
It's probably something with MATLAB. You know what? I think you and I had a meeting once where we were talking about something in MATLAB, and you had the same issue when I had MATLAB up.
Yeah, and I recall
Yeah.
though on a different meeting where it worked in the plots. So I've got, yeah, that's why you see two profiles of mine. One I'm remotely popped into my
Yeah.
computer, and it. So
Yeah, it's not important to see the code anyway. It was really just so you could see that this was code based on the EAU prime plus B, that it was the same problem, and to see that it's an approximation. So yeah, it really wasn't to go into detail of my horrible coding.
He doesn't want to show you.
Hey, I might
Right.
do it someday with my own finite element code. And like I said, two of those scripts aren't mine, so I can't give you guys the code. All right, well, we'll talk to you later.
All right, thanks.
Yep, see you folks.
Yeah.
See you.